Okay, hi, my name is Ingmar Posner. Thank you very much for having me. Uh, I'm a bit of a more practical sort of guy. I have the great privilege and the pleasure for the past sort of decade to be involved in this type of robotics, very much sort of mobile autonomy. We do a lot of work out in the real world amongst sort of real pedestrians, you know, dogs, people with children, that sort of stuff. We do kind of work with pods. We do sort of off-road driving, we do on-road driving, we do racetracks, we do kind of deliveries, all that sort of stuff. And when I first got into introspection, it was basically on the back of about 6 years of learning how to classify the world, segment the world. And around about 2010, I got really, really upset because I realized that despite being able to do all of that stuff, I still can't actually do anything with it. My robots can't act based on this. So in realizing that, you kind of get back to the idea that really robotics is a systemsy sort of thing, right? So we deal with systems where we have different sort of combinations of navigation, planning, mapping, so some data management, certainly perception, which is sort of where I live. Uh, and in each one of those, introspection is kind of relevant. But ultimately, what it boils down to is we try to get our robots to do a particular thing. Okay? And that's what I really, really care about. I want my robots to be able to do a particular thing. And of course, this is the glitzy stuff. This is stuff that everybody is used to, certainly get excited about, the sort of object detection in 2D and 3D, the semantic segmentation of the different workspaces. And I also was very excited about that. I'm still very excited about that. I've had, some track record in sort of inventing that sort of stuff. But what I really, really care about is how I can use this to actually make decisions, ideally safety critical decisions. Okay? And in doing so, I'll give you a little bit of a motivating example. And in doing that, I first of all will concentrate on perception, and then I'll talk a little bit about how that might apply in navigation. And some of the content here is very, very similar to what Rudy presented, and that sort of betrays a sort of a joint origin story, which is very nice back when Rudy was back in Oxford. Okay, so let me give you a motivating example. Okay, so you have some autonomous vehicle or whatever, and you try to kind of get it to drive down the road. Clearly, it seems that detecting traffic lights might be a useful thing, right? Let's just assume it is. Okay, so what do you do with that? Well, ultimately, you care about what the system does. So you stick this thing into decision theory, right? Where ultimately you compute an expected loss over some action given your state of the world. And then if you minimize that expected loss, you've got the action that you should take. The key thing is this guy here, right? Your expectation is simply a function of the loss and your assessment of the state of the world. And your assessment of the state of the world, typically at that semantic sort of level, comes from a classifier or some form of detector. Now, back in 2010, there was one moment when I read in a paper somewhere, here's the problem that we deal with. Now deploy the classification framework of your choice, because they're all kind of the same anyway, was sort of implied, and you will solve this problem. And to some degree, that is correct. Okay, so this happened way before we kind of got into the whole deep learning thing. So here are some of these sort of classification frameworks that people used at the time, Gaussian process classifiers, SVMs, linear, nonlinear boosters, etc., etc. And the point of that table is really not the detail. The point is to show you that they're kind of commensurate. And I'll show you this sort of precision recall curve where you might say this is terribly uninteresting, which it is because they're all kind of the same, according to those metrics. Precision recall, F1, whatever. All right. Let's think about a different metric. Okay. Let's think about this thing called normalized entropy, which in essence just tells you about whether something is a distribution is certain about one outcome or another. So we're kind of close to zero, or it's uncertain. Okay, it doesn't quite know what's going on, so we're closer to 1. Those are the only things you need to remember from this slide. Okay, let's think about that metric instead, and get back to that original example, because we chose it at the time, because each one of our classifiers that we looked at got that particular example wrong. Each one of those said this is definitely, or this is not a traffic light. Okay, and if we now look at the individual classifiers and we look at sort of the normalized entropy, we can see that some of them do that with pretty high uncertainty, whereas others, which are actually more common than the GPCs because they're much more efficient, get it wrong, but they're pretty certain that there's no traffic light there. That does not bode well for your decision theory, okay? Which is a beautiful thing, but if you put nonsense in, you get nonsense out. And typically I found that is where certainly my applications of this sort of stuff in the real world fell down. Okay, so going back to this question of what is introspection, and this is a very sort of subjective idea, and I think that it's probably changed about 3 or 4 times in the past 6 years. But what it boils down to, for me, it's really about knowing when you don't know. I don't really care right now about the philosophy of it. I don't really care about the psychology of it. I really just care about whether my robot has any inkling to tell me whether it knows when it doesn't know a thing, so I can take some form of alternative action. Okay? And there are a bunch of ways that I believe we can achieve this. So we can look at output generation, right, which is kind of the thing that I'll talk about a little bit in a second. Looking inside the box and saying, how do we actually generate these probabilities in the first place? We can look at output calibration, which has been around for ages. We can look at performance prediction, which is becoming more and more sort of on vogue now, and I'll talk a little bit about that as well. And we can talk about data vetting. Now, output calibration and data vetting themselves have a significant track record already in sort of in this game, even though it wasn't really called introspection, right? So output calibration, anyone who's ever used an SVM and got probabilities out has used probably something by Platt in 99, sort of a probabilistic calibration, essentially, of what comes out. There is a very kind of close relationship between this idea of output calibration and sort of performance prediction. And then, of course, there's data vetting, something like data integrity, people used to call it, particularly the guys down from ACFR, Huder and White. And some work also very recently out of MIT, Charlie Richter, who looked at basically predicting outliers from data, right? So that's another sort of interesting thing. I'm not going to talk about these two. Instead, I'm going to talk about output generation and also later performance prediction. All right, some basic examples. And Rudy's going to find this very familiar now. Okay, some basic examples. Okay, so imagine I've got a binary classification problem. I want to separate class 1 from class 2. And this might be, I don't know, stop signs, and the other one might be, I don't know, lorries prohibited signs. Okay? And I've got some test point that comes in that I want to classify. I have no idea what it is. And what do? Well, I train my SVM, say, or my deep network, say, which gives me a single discriminant more often than not. And based on that, in an SVM case, I look at the distance from hyperplane, for example. I'll make a decision. That guy is on the red side, so therefore it's clearly class 1. Right? It's class red. Okay. Problem is, of course, that this guy is actually not even in my set of hypotheses that I considered. Okay? So how do I deal with that? And that happens to us all the time, right? When I classify bicycle versus non versus everything else, it might be some guy on a mobility scooter, for example. That isn't really in any of my class descriptions, right? So what do I do with that? Okay. Well, there is an alternative view of looking at this, where first of all we think about all the possible hypotheses that we can have, the space n, and of those we only consider the ones that actually deal well with our training data, right? That gives rise to a thing called the version space, which is basically just everything that's in gray here. And note that there's a different shading here to the gray, which means there's some weighting here that goes on, right? Because some hypotheses might be more probable, some admissible hypotheses might be more probable than others, okay? So I'll only consider this version space. Now that's interesting, right? Because one of those guys might look like this, and so according to the distance from hyperplane sort of metric, I would say, well, this guy's clearly red. Okay, well, the other one might look like this, and according to the distance, that's clearly green, right? And this guy kind of goes straight through it, and that's sort of half-half, don't quite know. But, of course, I can combine all of those in some sort of meaningful way, and I'll come up with something that is mitigated against this, quite literally, predictive uncertainty. Okay, there are lots of models that explain this really quite well, okay, and they all get to vote to some degree. Of course, that voting is via Bayesian averaging. Okay, so we have our posterior predictive, which is kind of this guy, the thing that we're trying to say, that we're trying to call, what kind of class it is, and literally we average over version space, right? And we do that in such a way that we also have some idea of how likely a particular model is. Now, that implies that something like a non-parametric method, like a Gaussian process, can do this really, really well, because this is what they live and breathe, okay? This is what a Gaussian process does for you. It integrates over all possible models. Okay. All right. So that's interesting, right? Because that would then imply that Gaussian processes or non-parametric models are really quite good at this. Not the only ones, by some distance, I hasten to add. But there's now a working theory of what might be useful sort of in introspective classification. All right, well, let's have a look at this. So we've done a bit of an unfair test, right? So we trained bunch of our classifiers on two classes, flourish, prohibited, and stop, and we test, and it turns out that everything's really quite certain, right? So this normalized entropy across here, 0 here, 1 there. So everything's nice and certain, which is good. Then we show it this sort of random other class, okay? And we suddenly see that actually, if we look at the SVMs, they're kind of somewhat uncertain, but not terribly. The linear SVMs are all over the place. The Gaussian processes are kind of slightly better. Might be marginal, but slightly. But there's a trend, right? Because as we repeat this experiment with lots of different combinations of known things and unknown things, we find that more often the Gaussian processes, the non-parametric methods, tend to be more uncertain about things that they can't possibly know. There's no right answer to this experiment, other than, actually, I really don't know, ideally. Okay? And implicitly, what's happening here is some conditioning on the training data that was seen during the training of the algorithms. Okay? And often, when we look at classification frameworks, that completely gets lost. Okay. And of course, numerically, forget the density of the table. All I'm trying to show you here is this is the same experiment, just the numbers, lots of different trials. This is mean normalized entropy. Note that every time the sort of non-parametric model wins in terms of how much it doesn't know. Okay. It wins in saying I don't know. There's also, very interestingly, a gradient here, right? Because if you look at the numbers, these guys look, the GPCs, the non-parametrics, are very, very uncertain about these guys, but they're much less uncertain about this guy. So there's also something visual going on here in terms of the appearance of what's going on. That actually that 70 limit sign is kind of close to what it's seen during training. It's not the same thing, but it's closer than something that's blue and has an arrow in it. Okay, so that's sort of an interesting thing. How uncertain does it need to be? Well, I don't know, but I can ask my system, because my system has to provide some form of function, and so I can let the system decide what might be useful. If we go back to this traffic lights idea, this is sort of the last slide on that I'm going to show. What we have here is the same sort of idea, but in the classification setting, or in the detection setting, where we're saying, well, find me my traffic lights. And this is a bit of an unusual graph, where here we've got false positives, and false negatives, and false positives. Here we've got normalized entropy. And similar to something that Rudy said earlier, if you had something that was perfectly introspective, that would only make mistakes at 100% uncertainty, you would live down in that corner here. Okay? And again, at this in this sort of traffic light detection task, you can see this sort of relative ordering of the non-parametric method going out from here and then all the other situations. Okay. There's a quick thing that I wanted to say in terms of the tale of two extremes, and I thought Rudy was going to touch on that earlier, which is actually for me a bit of an aha moment when we did this work. So on one hand, you've got this one-shot classification idea. On the other hand, you've got this marginalize over version space, right? Integrate the whole thing. But of course, there is a middle way, which are sort of ensemble methods or mixtures of experts. Okay, so it turns out that you can look at this view not as saying I want to integrate over the whole thing, but as saying, I'm just going to take a couple of these guys, and I'm going to place them through version space in such a way that I get a good idea of the predictive uncertainty that helps with efficiency. Okay, I just want to throw that out there as an idea that you might want to consider at some point. Okay. Oh yeah, so the whole thing becomes discrete. Fine. Okay, now we published this in 2013, it says, and we're pretty happy about that simply because that was one of the sort of early papers that looked at classification frameworks and how they lend themselves to sort of safety critical decision making. So that was nice. I can't really summarize all of Hugo's, the guy who did this work, Hugo's thesis here in this talk, otherwise it would take forever, and there's some other stuff I'd like to touch on. So I decided to do it on a single slide instead. But there's some really interesting stuff in there. So for example, the effect on one-shot decision making. It turns out that introspective methods are more faithful to the actual cost profile. So it doesn't matter if I make running someone over infinitely costly, right? If my overconfident classifier says, or detector says, there's definitely nobody there, I'm still kind of screwed, okay? So you can very quickly arrive at an intuition why introspection in that case is useful. And there are lots of results like that in Hugo's thesis, as you can see right here. No classifier is perfect. So none of the frameworks that we tested back in Oxford were actually usable, frankly. So again, there's a system side where we mitigate against this, where we build systems that act out in the real world. But if you just wanted to act based on classification output alone, None of those were usable. But what does it mean? What's actually useful? So what's a perfect classifier in that sense? And again, it turns out when you look at that sort of thing, the entropy of the error profile turns out to be very, very interesting. Okay, so again, I'll refer you to Hugo's thesis with that. And then what about sequential decision making, right? And again, it turns out that there are lots of results in there that show during sequential decision making, introspection actually helps to be more efficient at performing a particular task. Okay, so might be worth it. Okay, performance prediction. And I'm pretty sure Marshall is going to tell you much more about that in a second. Let's think about that again from the context of decision making, right? I'd like my car, my vehicle, my robot to decide when it can operate and when it can't. And this time, I'm going to exploit some other aspects of the system that I'm going to deal with. Okay? So typical issues that we have is we go out and we say, well, is this safe to drive? Different conditions. Okay? And I'm pretty sure some humans who can look at humans who can look at some of these, and we can go, well, actually, for my vision-based classifier, that looks a bit dodgy, right? Overexposure, underexposure, these are sort of the typical failure cases where we go, it's not particularly useful. Okay? So wouldn't it be nice if there was some system out there that basically says, you know what, in terms of data vetting or in terms of performance prediction, in this place or looking at this particular piece of input, I don't think you're not qualified to say anything useful here. And note that I've now stepped outside the classification framework and into the system. And I've introduced sort of another concept that says, actually, there's some guy who says, looking at the data here, don't trust it. Don't trust the system output. Okay? So what we can do is, again, look at this from a decision-making point of view. We've got actions, offer autonomy or deny autonomy. We've got some states, which is, hey, my perception system is functioning or my perception system is failing. And again, we kind of look at the loss that we define, that we can write down. And again, we minimize the expected loss. And again, it boils down to getting our assessment of what the state actually, what the state of the world actually is. All right. So the next couple of slides are really only about unraveling this guy. Now, imagine that you have a system. So okay, robots tend to operate in the same workspace, right? In one workspace that they operate in for a long time. Imagine that you have a system that knows where it is, so you've got a localization system that kind of tells you where in that workspace you are, and you kind of repeatedly go through that. And because you know where you are, you can attach image data to it and performance criteria. Okay. And it may well be that here you get a whole bunch of false positive detections, so that's that place, and here you kind of get a whole bunch of true positive detections, so that's that place, and that's nice. And of course, you need to know whether something's false positive or true positive. So you've got some oracle. You either have somebody label some parts of your data set, or you use an alternative metric. Right? You have some other oracle, some other sensor that is better that you don't usually carry with you. Could be any of those. And then you basically count. Okay. So you say, you know what? Every detection is an event, and my false positive and my false negative is a 0 event, and my true positive is a 1 event. Okay. My events, the Zs, are Bernoulli distributed. We call this particular thing a performance record because the Bernoulli distribution with mean theta is different at every place that we consider. Okay. That's why is that nice? Because ultimately we can actually incorporate observations like mu Zs for a particular place, simply by the Bayes rule. And of course, to make the whole thing nice, we use a conjugate prior, which is the beta prior for the Bernoulli distribution. Okay. So all of that makes the math really quite nice. Note that I could have taken exactly the same slides, exactly the same slide, and talked to you about flipping coins. Okay, it's exactly the same idea, right? It's just that basically what we're asking here is, as I get to a particular place, in the coin flip of my detector saying, hey, here's the thing, is this more likely to be 0? Yeah, false positive, false negative, or is it more likely to be 1? Some form of true detection. Okay, and what we're trying to do is, from experience, literally learn what those distributions are, what those biases are, those coin biases at a particular place. Okay? And so our probability of failure is actually in this sort of feature space, where we're saying probability of failure is simply according to some threshold that we set by hand, as you would typically do, the probability of this area here under your beta distribution for a particular graph. That's it. Okay? All right, so what does that look like? Well, in the space for where we got most things wrong, our beta distribution is going to be heavily biased towards 0, as in lots of wrong stuff, okay? In the place of all good, we're heavily biased towards 1, as in, useful stuff's kind of coming up. Now, so far so good. The problem with that, of course, is that you need to somehow account for lots of different visual variation. Okay, so you need to figure out what makes a place for this particular place. So you can look at this different sort of scene, so this is all the same sort of place, and you can go by location. So you put a localization, put a radius around it, or a GPS radius, or whatever you choose. Okay? But of course, you're going to struggle with that because your appearance is going to be vastly different, and so your vision-based classifier is going to, detector is going to struggle. Okay? Or you could just go by appearance, whatever fashion you go by. Okay? You could only choose. You could, for example, decide to use experience-based navigation or a DAP4 system or anything like that will give this automatically, or you could do an external sort of matching, clustering sort of thing. Okay. We've taken this out. We have gathered about 60 kilometers of driving data from a place called Milton Keynes, which I can heartily recommend to anyone who wants to come to the UK. A couple of giggles by people who've clearly been there. Okay. About 70,000 images. And I don't want to dwell on this for too long, but here's basically what that graph shows. So here we've got the percentage of mistakes, and here we've got this sort of tau threshold. We've got two sort of benchmarks here. One is always on, always say yes to autonomy. The other one's always say no to autonomy. And the way to interpret that is to say that, well, actually, if my tau threshold is 0, that's the same thing as saying failure never happens, right? Therefore, say always on. Okay, so that's why we throw inside over here. If my tau is 1, I'm basically saying, unless everything is super perfect all the time, say no. Okay, which is what these guys throw inside over here. Now, the interesting thing here is, of course, that both of these lines, so if, red and blue are appearance-based and sort of location-based, respectively, both of these drop below the always yes line. They kind of essentially they achieve the lowest percentage of mistakes. Okay, that in itself is already an interesting sort of outcome, right? There's also something interesting going on in terms of the gaps here, because here appearance versus localization clearly makes a difference. Okay, so in this particular case, we use sort of ACF features with a linear SVM, which is was fairly common until about 2-3 years ago. And that limited capacity SVM model really struggled with that feature mix, sort of in the localization-based approach. Okay? Over here, what we see is percentage of route offered in terms of autonomous mode. Okay, and so it turns out that both of these give you a certain fraction based on tau, but the appearance one actually gives you a higher fraction of the route-driven autonomy. Okay, it's kind of what you would expect. Here's exactly the same thing, but for a deep network that was sort of state-of-the-art on actually probably a year ago or two. The margins are different here, but the idea is basically exactly the same. One thing I'd like to point out is that the difference here between appearance and localization-based is much narrower. I mean, they're both still outperformed based on decision-making, hooray, but the difference is much narrower. The margin is much smaller, and that's because the deep network clearly caters better, or copes better with the appearance variation that you get from the location-based approach. Oh, that's just. Okay. All right. And interestingly, what pops out of that system then in the end is, a very interesting sort of classification of benign places versus tricky ones. So up here are places where the system goes, you know what, I'm pretty confident that the perception system is going to work here. Down here, we have a system that we have places where basically the system says, it's going to be slightly tricky. And in there, we also find examples of those typical ones that we would also single out as overexposed or underexposed or shadowy. So. Okay. Another way of doing this, the last way of doing this, is to, again, look at a navigation task, but this time actually look at a navigation task proper and not the perception bit. And look at something like a visual teach and repeat system, okay, which is pretty much a workhorse for things like planetary rovers and can be used and redeployed in sort of warehouses, bookbox systems, etc., etc. So this sort of stuff is everywhere. And it crucially depends on matching your live view to your memory of what it is, your teach path. Okay? Now, a while back, we did some work on energy management and switching the sensors on and off on a Mars rover to actually save energy. And the trade-off that you make there is deviate from teach path versus expending energy to stay on the teach path. And the question that came up was, well, how far can we deviate? And the answer was nobody knew. So we set ourselves that challenge and said, well, actually, can we predict the trust region for navigation? And we did 2 iterations, one where we measured it and one where this is like a predictive system. And the question here is, so can we predict the sort of localization envelope where this guy here is your reference path? How far can we deviate from here, right? And what we're going to do is exploit existing traversals to build a model in a self-supervised manner. Self-supervision, massively important for systems that run out in the real world, particularly in the context of sort of what we do it, we use it over and over again. And in those days, which was, it says 2016, but it was mainly sort of 2015-ish, we leveraged a GP to regress onto that function. Okay? Very briefly, what does that look like? Well, this is what we try to do, pretty basic. We have our teach path, we have a query point of that teach path, right? We want something, y, that kind of gives us some idea of how well we can localize to this keyframe, right? And of course, because it's based on these visual features, our y is the number of keyframe features matched. We're trying to predict the number of keyframe features that we're likely to match from a given position. Okay? F here, as I said, is a graphic process, and the features that we use is basically keyframe appearance type of words, so that's this guy here. He says probably fairly old school, but hey. Distance from path and the local path curvature. Okay? And what that looks like in practice is like this. So we go around some environment, that's our first teach path, and then we repeat. And we repeat more. And this is done autonomously. So the repeat paths are basically the vehicle driving around, okay, following the original path with some deviations. But we can measure those, right? And from that, we can basically measure a model where red says, hey, lots and lots of matches, all is great, which happens to be somewhere in the middle. And sort of the bluer it gets, the worse the sort of localization performance is likely. And so the nice thing about that is, as long as we're sort of in the same sort of environment, parks, urban, whatever, right? We can take we can train on some route, come up with this model, but we can predict a different route, right? So now what we can say is we get the sort of reference trajectory in, which is a sequence of images, and we can then predict how far we can deviate, which we can then put in some sort of plan. Okay? But again, the idea here is that you have your teach path with your prediction and your ground truth, and here's another one. So you teach on one, and you predict. And teach here is a bit of a misnomer. This is teach as in this is your reference path. So you go out, you get your reference video, basically, and you shove it through your GP, and you basically get an idea of how likely you are to localize, depending on how far you deviate. Okay, so that's probably the whirlwind tour of what I wanted to give you. A couple of sort of take-home messages that I think are quite interesting for me, certainly. Introspective is a key aspect of robot learning. So in the title of this presentation, I really, I said it's robot learning at its best, and I stick by that simply for one reason. It is something that comes up because we have robots operating out in the real world. Okay, so the reason why this had relatively little attention in machine vision and in machine learning is simply because when you misclassify a plane as a cow, you might not get your paper in the CVPR. When you misclassify something not being in front of the car, right, that has pretty dire consequences. So it's inherently a robotics problem. It's inherently a robot learning problem, and I find that really quite pleasing. Introspection can take many forms, so I don't really want to get too hung up about what philosophers say. As long as, for me, certainly, we get back to this question of knowing when you don't know something, knowing when you have to take some remedial action. You can look within. Not all classifiers are equal. Many are wildly overconfident. We've covered this. Non-parametrics are pretty good, but we haven't yet actually found a real one that will do. So we have some theories and a whole bunch of results, and Hugo's thesis, about what a perfect one, what a good one may look like, and how good it needs to be to perform a particular task within a certain limit. And you have to look without. So systems that are basically watchdog systems where you can either calibrate, but of course, non-stationary environments like the ones we act in, that kind of hurts. But the workspace is your friend. The robots tend to, more often than not, operate in particular workspaces over and over again. They don't operate everywhere. And those workspaces tend to only show you so many faces. Okay? And that's quite useful when it comes to this. And again, statistical data, I think, might just do the trick. Charles Richter from MIT has done a great job on that, so I certainly would recommend you look at his work as well. Also, we're having this workshop. Introspection now is certainly mentioned almost everywhere. So we seem to agree that it's an important problem. Whether we've pinned down exactly what it means is a different question, which kind of makes it a bit weird like that, right? But I have a pretty good sense of what it means to me and what I'm trying to achieve with it. And with that, thank you very much.
Thank you very much for the talk. Any questions? Yes, please.
Hey, thank you for your talk. Can you maybe I missed it, but what is the intuition again for why not?
It's the fact that inherently methods like GPs, they integrate over your model space, in particular in a weighted sort of way. So every hypothesis gets a weight. And I'm not saying, hey, this is why we should all use non-parametric methods. I am saying that's actually a pretty decent explanation for why they do better at what we're trying to do.
I was wondering because the non-parametric nature of them means that they have like you can assume infinitely many parameters and so on. Is that also one of the?
No. They don't necessarily have to. They don't necessarily have to assume that. I think if you take anything away from this, one thing that is more intuitive is that for a non-parametric method, you keep the data around. And one way of telling this introspection story that I could have also told is to say, well, actually, you want to condition what you see right now, or you want to condition what you say right now based on your test data, on how that test data relates to what you've seen during training, right? So that's the same sort of idea. That's the same sort of idea.
Any more questions? We have time for one more. Yes, please.
And then immediately you said, okay, we focus on the classification problem because this is the most important.
Did I say most important?
Well,
if I did say that, I wasn't.
Based on what we actually see, like how we classify, and you get the method based on that. My question is, is it the case for particular application you're mentioning, like a driving car, or any robotic system you can imagine, and you can explain just by like introspection in the classification of the machine learning method is the most important aspect of introspection for robotics.
Okay, so this is coming back to me now. So I said for me, it's the most important bit is sort of introspection perception, simply because this is where my background is. Okay, I would like you to erase from your mind for now that I've talked about the context of autonomous driving, right? Because in the context of what I'm saying here, it really doesn't matter. Ultimately, I mean, it's more powerful when we talk about safety-critical decision-making, which is what this is for, but it applies to decision-making, right? If you want to be able to act based on your assessment of what the environment looks like, whether that be a classifier or a segmenter or whatever it is, right, then you need to have some form of idea of when your assessment of what the environment looks like has failed. Okay, and that is really what the story is about. I have no idea whether that even touches on your question, but it's like this is not tied to autonomous driving, and I wouldn't even go as far as saying, "Oh, perception is the most important problem right now." Even though I personally, in my life, in my everyday working life, I find that it's probably one of the key stumbling blocks that we deal with right now. But I also know why that is, and that's because whatever performance measures, whatever confidence measures, probability or otherwise, come out of my perception system right now, totally useless when it comes to actually robustly acting on it. Does that?
Yes.
Could you elaborate a little more about the calibration you use for that's not stationary curves?
Okay, so I could basically, how do I best do this? Okay, trivial example, imagine you live in a world with only like 5 objects in it, right? And you really calibrate your output according to those 5 objects and say, when my classifier says 0.3, it really means 0.5, okay? And then you transition into a world where there's another sort of 3 objects, right? and it turns out, or object types rather, and it turns out that your calibration is kind of it's somewhat meaningless in that sort of new world. That's a bit of a crass and a bit of a crude example, but in reality we find that a lot. So for example, I could calibrate. I could take lots and lots and lots of training data of 3 o'clock in the morning, of driving a vehicle around 3 o'clock in the morning. Okay, and I could say this is my 3 o'clock data set. Okay, and I train my classifier on that. And then, say it's 3 o'clock in the morning, and if you're in Britain, it's pretty dark and miserable, right? So, say you then go out at 10 o'clock in the morning. This is where the Britain analogy falls down, but let's assume it's nice and sunny, okay? It's now 10 o'clock in the morning. There is drift, right? There is drift in that. And it turns out that there are some other ways of dealing with this. For example, Marcus over there tomorrow is going to talk about how we do that, how we look at that in the context of domain adaptation, right? So that's sort of cool as well. But there is drift, right? And so your calibration for 3 doesn't really match what happens.
So thank you very much.